Hey everybody, Dr. A here, and in this video we're going to be exploring another example of normal strain. So let's take a look at what we're given. Here we're being told that the normal strain in a rod is given by the function epsilon is a function of z equals 50 times 10 to the minus 3 times the square root of z. So you notice that this is a strain function and it's a nonlinear function because you've got square root of z in as the function. So z is your independent variable, epsilon is your dependent variable, and of course you have epsilon as a function of z. And z is given in meters, okay? This triple equal sign means has units of meters. Compute the displacement of the rod at point A. So here's our diagram. We have this rod that is fixed up at a ceiling at point B. Z is measured from that fixed point downwards. So this fixed point is like the origin. The original length of the rod is 300 millimeters, and point A is the free end, and you've got some kind of applied load that is causing some kind of deformation or strain happening. Now, we're not really interested in this load. We're just, because we're given what the strain function is, okay? This load is just here for the sake of showing what could be causing that strain, all right? So let's go ahead and start solving this problem. Now, we know that the basic definition of strain is a deformation over an original length. That's the basic definition. And we also know that we can rewrite this as L prime minus L naught over L naught, where this L prime is the total final length, deformed length of the member, all right? But again, we have a function here, all right? Epsilon is a function. It's not just a constant like we saw in our other example, all right? Because of that, we need to use the differential form of the definition of strain. So I'm going to make a note here. I'm going to say use the differential form of strain since we have a function for epsilon, okay? And so what would the differential form look like? Well, we would say epsilon equals, and using the variables we have here, we can say dz prime minus dz divided by dz. Okay, and again, I'm using z here because we have z as our independent variable that represents length, okay? And so if I do some rearranging here, I can solve for dz prime. Now, why am I interested in solving for dz prime? Well, the reason is because the problem asks us to compute the displacement of the rod at A, okay? So we're given epsilon, we're given strain as a function, and we want displacement, which means we're going to need to get some kind of information of dz prime or this entire numerator for that matter, okay? So how do we do this? Well, this is a differential equation, and we're just going to separate out the variables because this is just a separable differential equation, okay? And so by doing a little bit of rearranging, I can get dz prime equals epsilon dz plus dz, okay? So I have separated my variables, z prime and z, all right? The next thing I'm going to do is I'm going to just go ahead and say dz prime equals epsilon plus 1 quantity times dz. How do I know that? Well, I just factored out a dz from each one of these terms that I'm adding together, all right? So now what I can do is substitute my function in for epsilon, all right? Remember, we had that function. So I'm going to say dz prime equals, I'm going to say open parentheses, 50 times 10 to the minus 3 times the square root of z, and then plus 1, that plus 1 is this plus 1 here, close parentheses, and then dz, okay? So how do I solve for z prime ultimately? Ultimately, I'm getting the information about that deformed length. Well, I just take the integral of both sides of this differential equation, okay? And it's a separable differential equation that we've already separated. So I'm going to say z prime equals the integral from 0 to 0.3 meters of 50 times 10 to the minus 3 square root of z plus 1 dz. Now, why am I integrating from 0 to 0.3? Well, the domain of this function is from z equals 0 to z equals 300 millimeters, but we were told that the function, inside the function, z has units of meters. So because of that, I need to make sure instead of using 300 millimeters, I use 0.3 meters, all right? So we perform this integral. Now, this is a definite integral. It's a pretty easy one to perform. I'm going to actually do this in my TI-36X Pro calculator. I love this calculator. I strongly suggest that you use one. It's a great calculator for engineering students, especially when you're getting ready to take the FE exam one of these days. All right. So I'm typing this in my calculator as I'm speaking. And I'm typing times. In your calculator, you have to use X because they don't have Z for you in that calculator. Let me try to type that one more time. It's good to practice this. Again, when you get ready to take that FE exam, you can't use a graphing calculator, so you need to get used to using an approved calculator, which a TI-36X Pro is an approved calculator. Okay, so I punch this in my calculator and I get 0.3055 meters, okay? And that is a deformed length, and it's gonna deform downwards. It's gonna be a tensile type of deformation, so it's gonna have a stretching effect, all right? Now, am I done? Am I done? Almost, not quite though. So this Z prime value is the total deformed length. So let's think about it. The original length was 0.3 meters and it deformed to a final length of 0.3055 meters, okay? So what would the actual deformation or the elongation of that point really be? Well, we can say that's going to be delta equals Z prime minus L naught, all right? And so that's going to be 0.3055 meters minus 0.3 meters. And so what do we get? We get 0.005477 meters. So that is our final answer. Now that's a really small number. When we have small numbers, we sometimes like to use more appropriate units. So you could express this as 5.48 millimeters. Again, if you're studying for an FE exam or a multiple choice exam or test, you want to be careful with how the question asks you to express your answer. If the question says, what is the value in millimeters, then you would use 5.48 as your answer. If it asked for it in meters, you would use the 0.00548 meters as your answer, okay? But again, this is the deformation. This is the displacement of the rod at point A, okay? Well, thanks for watching. Hopefully you found this helpful. If you did, please hit like and subscribe and check out some of my other content on these topics.